Today we're going to be talking about polynomial curve fitting, or polynomial interpolation if you like big words. So all it is this. If you have 2 points in the plane, you know that there is a unique line which those 2 points lie on. What about other curves? Suppose you have some higher number of points. Is it possible that there is a unique cubic curve or a unique parabola or some higher order polynomial going through those points? If so, how do we find it? And maybe even a deeper question, how is this actually a problem for linear equations? More precisely, suppose we have n points, x1, y1, x2, y2, all the way up to xn, yn, n different coordinate pairs in our two-dimensional plane. Can we find a polynomial p of x of any degree which goes through all n of these points? So our polynomial is going to be some coefficient times x to the m plus some coefficient times x to the m minus 1, all the way down to a1x plus a constant, and m, we want to determine what is a suitable m given that we have n points. Is there a relationship between those two numbers? And in fact, yes. Notice that our degrees of freedom, which is the key concept here, the degrees of freedom in this polynomial are these coefficients. How many of these coefficients are there? Well, there's 1 through m, and then there's a0. So there's going to be m plus 1 coefficients in our polynomial. And we have n points. This essentially means that if we were to have less than m equals, suppose we have m less than n minus 1 degree of our polynomial, then we're actually not going to have enough degrees of freedom to account for all of these points. If we have m greater than n minus 1, strictly greater, we're going to have too many degrees of freedom in our polynomial, and we'll be able to find a polynomial that goes through all those points but not a unique one. In fact, there will be infinitely many polynomials which go through all those points, as you'll see. But like Goldilocks and the 3 bears, if we choose m is equal to n minus 1, it will be just right. So how do we do this? Well, for the polynomial to pass through a point given by this coordinate pair, that is to say that that coordinate pair belongs to the polynomial, in the sense that if you plug in xi, the x coordinate, into our polynomial, we should get out the y coordinate, right? Y sub i. All this means is that at the input xi, our polynomial has height yi, right? Our polynomial passes through this point. That's exactly what we want. And we want this to be true of every point, not just one. But for this, we have a formula, right, in our unknown coefficients. So suppose we pick the point x1, y1, our first point that we wanted to go through. Well, we'll have a0 plus a1 x1 plus a2 x1 squared plus a3 x1 cubed plus etc. all the way up to a sub m x1 to the m is equal to y1. Now notice with this equation that although this looks like a polynomial equation, it's really a linear equation. Why is that? Well, our x1 and our x1 squared and x1 cubed and our x1 to the power of m, whatever m is, it's going to just be a number, right? Because we're picking specific points that we want our polynomial to go through, which means x1 and y1, or xi and yi for any I, are always going to be specific concrete numbers in these problems, which means that this is not actually a polynomial, this is actually a linear equation. But what is it a linear equation in? Our unknown coefficients. We have a number times our unknown, a number times our unknown, a number times our unknown. And notice that this has to be true for all of our points, not just one. So let's write this out. Well, this means that we also have to have a0 plus, for the point x2, y2, a1 x2 plus a2 x2 squared plus a3 x2 cubed all the way up to a sub m x2 to the m is equal to y2, right? Another linear equation. And this has to be true for all n of our points, so that we'll have all the way up to a0 plus a1 x sub n plus a2 x sub n squared plus a3 x sub n cubed, all the way over to a sub m x sub n to the m is equal to y sub n. So what we have is, by the condition that our polynomial has to go through all n of these points, we have exactly n different conditions in the form of linear equations, so a system of n linear equations dictating what our coefficients a0, a1, a2, etc. have to be. And so the only question we have to ask ourselves is, what should m be, what degree should this polynomial be, such that the system of linear equations has a unique solution? So the only thing we need to figure out is, what should m be, right? What degree polynomial do we need in order for this system of linear equations to have a unique solution? And it will be, as I said before, m is equal to n minus 1 will give us a unique solution so long as we don't have any points which fail the vertical line test, because no function is going to pass through both of them by definition. So as long as we don't have that, as long as we don't have any repeat points, so we can't have 2 points being the same point, right? So if we have n distinct points which pass the vertical line test, then a degree n minus 1 polynomial will give us an n by n system of equations, a system of equations in n unknowns, notably our coefficients a0, a1, a2, all the way up to a sub n minus 1, and this will give us a unique solution, a unique polynomial. Okay, so what does this actually look like? Well, we're going to start with our n points, our n coordinate pairs. Then we're going to form this system of equations using those pairs and our unknown polynomial, right? Then we're going to turn it into an augmented matrix, which is going to look like this every single time. This is also called a Vandermonde matrix, if you're interested in that. 1, x1, x1 squared, etc. x2, x2 squared. It's straight from this, right, where each column corresponds to a coefficient of, or various coefficients of a0, a1, a2, all the way up to a sub n minus 1, and then of course in this partition is our constant terms. Right, so we form the augmented matrix for our system of linear equations as we've been doing, and then you can use your choice of either Gaussian elimination or Gauss-Jordan elimination in order to row reduce and solve this system of equations for these unknown coefficients. Once you've found those coefficients, you plug them into the polynomial and you have your final graph. Let's do an example of this. So we have these 4 points and we'd like to find a unique polynomial interpolating this data set. So since we have 4 points, we're going to want n minus 1, which is 3, as the degree of our polynomial. So we're going to look for a unique cubic curve going through these 4 points. So our polynomial p of x is going to be some unknown coefficient plus another unknown times x plus unknown times x squared plus an unknown times x cubed. All right, now let's form our system of linear equations by plugging in all 4 of these points into our equation here. So first, this point will have a0 plus a1 times 0, which is 0, plus a2 times 0 squared, which is 0, plus a3 times 0 cubed is still 0, is equal to 3. Now our second equation coming from that point is going to be a0 plus a1 times 1 plus a2 times 1 squared plus a3 times 1 cubed is equal to 1. Third equation, we're going to have a0 plus a1 times negative 1 plus a2 times negative 1 squared, which is just 1, plus a3 times negative 1 cubed, which is negative 1, is equal to negative 1. And our last equation is going to come from that last point. a0 plus a1 times 2 plus a2 times 2 squared plus a3 times 2 cubed is equal to 5. So this is our system of linear equations. We could write it a little bit more neatly, and I'll rewrite it here, and then we'll put it into augmented form, augmented matrix form, and we will start row reducing. Okay, here's the system rewritten a little bit more neatly. Here is the augmented matrix straight from the system, and now we can start row reducing. So what do we want to do first? Well, row 1 looks pretty good. So let's add the negative of row 1 into rows 2, 3, and 4 all at once, just to save us some time rewriting. So we'll have 1, 0, 0, 0, 3. Then we're going to have 0, 1, 1, 1. And we're going to have negative of 3 plus 1 is going to be negative 2. Then we're going to have 0, negative 1, 1, negative 1. And then negative 3 minus 1 is negative 4. 0, 2, 4, 8. And negative 3 plus 5 is positive 2. All right, so that was our first step. And what should we do next? Well, let's add one of row 2 into row 3. So if we do that, we will get 0, 2, 0, and negative 6. All right, that's looking pretty good. Now let's do something similar. Let's take row 2 and add negative 2 of that row into row 4. So we have 1, 0, 0, 0, 3. We have 0, 1, 1, 1, negative 2, 0, 0, 2, 0, negative 6. Actually, while we're at it, let's also divide this row out by 2 to get 1 and negative 3, just to save us some time. And then we're going to have 0, 0, negative 2 plus 4 is 2, negative 2 plus 8 is 6, and positive 4 plus 2 is going to be 6. All right. Let's next take negative 2 of row 3 and add it to row 4. So 1, 0, 0, 0. 0, 1, 1, 1, 0, 0, 1, 0, 0, 0. That'll be a 0. And that'll stay 6. Negative 2 is, that'll make a positive 6. Plus 6 is 12. And then let's actually also in this step, let's divide this last row out by 6. So we'll have 1 and 2. All right, we're getting close here. I've rewritten our matrix up top here. Let's continue. Next step, let's add we're going to do, we could do Gaussian elimination at this point, but I would rather practice our Gauss-Jordan elimination. So let's take this row and add a negative of it to row 2. So 1, 0, 0, 0, 3. So that will be 0, 1. That'll be a 0 now. That will still be a 1. And positive 3 plus negative 2 is going to be just a 1. All right, we're almost there. One more step. Let's add the negative of row 4 into row 2 here. So that'll give us 1, 0. We'll get a 0 there, and we'll get negative 2 plus 1 is negative 1. Right? And now, this is as simple as our system can get. And notice that we have a 1 in each position, representing an A0 is equal to 3, A1 is equal to negative 1, A2 is equal to negative 3, and A3 is equal to positive 2. So that means that our final polynomial is going to look like P of x is equal to 3, well, let's write from highest degree downward. It will be 2x cubed minus 3x squared minus x plus 3. And the question we have to ask ourselves now is, does this polynomial go through all 4 of our points? Well, there's one surefire way to check this. We can plug them in. So our points, if you recall, are going to be 0, 3 first of all. So does 0, 3 belong to this polynomial? Well, if we plug in 0, 0, 0, okay, we'll just get the 3. So yes, 0, 3, we are good there. Our next point is 1, 1. Plug a 1 in there, a 1 in there, and a 1 in there. We're going to get 2 minus 3, which is negative 1, minus 1, which is negative 2, plus 3, which is 1. We're good. All right, our third point was negative 1, negative 1. So we're going to have negative 2 minus 3 is minus 5, plus 1 is minus 4, plus 3 is negative 1. We're good on that point. And our final point was 2, 5. So this is going to be 16 minus 12 is going to be 4. Minus 2 is 2, plus 3 is 5. And our polynomial does indeed go through all 4 points. And if you were to graph this too, it's going to look something like the following. You would have, so if we put our points on here, 2, 3, 4, 5, then we would have 0, 3 is right here, 1, 1 is right there, 2, 5 is all the way up here, and negative 1 is right here. And our polynomial, P of x, if you were to graph it, would look a lot like this. And so we have indeed interpolated our set of 4 points with a cubic polynomial. All right, now that's all well and good, but let's be honest, cubic polynomials are child's play. We need to up the ante. So here we are in MATLAB, and we're going to do the same thing that we were just doing by hand, but I wrote a little script which will do it for us on the computer. And the advantage of this is, of course, that we can do more points, higher order polynomials, bigger matrices. You don't want to be sitting around row reducing a 20 by 20 matrix using Gaussian elimination all day. No, we don't want to spend our time that way. So that's why we have MATLAB and similar things like it, so we can scale up our algorithms a bit. So toward that end, we have, I wrote this, we have n equals 5 is the number of points. So we can pick any number of points we want. We can pick the size of the interval, and what it's going to do, it's going to set up our coefficient matrix for us. It's going to solve for those polynomial coefficients, and then it's also going to graph everything. It's going to graph our final polynomial along with the points that it interpolates, and it's pretty straightforward. Like I said, the great thing about doing this on a computer is that you can do much more intense problems this way. Scalability. So let's see what happens when we run this. So I'll just do run polyinterp. See what happens. We get, here are our 5 randomly chosen points, and here is a polynomial going through it. That was pretty fast, huh? We should do that again. Why not? It's kind of fun. It's satisfying. Very nice, very nice. Can we do more than 5? Sure, we can do more than 5. Let's do 10. Let's save that. Ten randomly chosen points and a lovely polynomial, or at least we see part of the polynomial, going through those points. Wonderful. How about 20? You wouldn't want to be doing this by hand, let me tell you. Look at that. 20 different points, and we found a polynomial that goes through all of them. However, MATLAB has given us a warning this time. It says matrix is close to singular or badly scaled. Results may be inaccurate. Is this just a coincidence? Let's try it again. No, this is not a coincidence, as we see a second graph here and the same warning. Now what's happening here is two things. Something that you, if you're just learning matrices for the first time, are not yet familiar with, is the problem of numerical stability. This is not something we're going to talk about in detail, but I want to bring it up just because you may encounter it later. So there are two problems here, as far as I see. Problem number one, when we randomly pick points in this interval, we sometimes, actually we quite often get points whose x-coordinates are very close to one another relative to the other numbers in this problem. So you see there's almost a vertical line going between them. And remember that we said that whenever there's a vertical line going between 2 points, if they have the same x-coordinate, then we can't use this algorithm, right? It won't give us the right answer because no function can do that. No function can go between 2 points which have the same x value but different y values, because a function only has one output for every input. So that's part of the problem. And then another problem I'd like to bring up is just that as you scale up algorithms, you start to run into issues, especially with matrices. The determinant might get close to 0. We don't know what the determinant is yet, but the determinant, that's what it means when it says that it's singular, it doesn't have an inverse, or it's very close to not having an inverse matrix. And Gaussian elimination famously is bad on computers for huge matrices because errors compound very easily in Gaussian elimination unless you make some small adjustments, like adding what's called pivoting into your algorithm. So anyway, the point is that there are numerical considerations you have to take into account when you try to scale algorithms like this up a lot. And MATLAB's solver, which is essentially happening in this line, is much more dynamic and robust than Gaussian elimination, but we can still run into problems when we use a huge number of points, and again with the problem with points almost being on top of one another. So if I plug in n equals 50, you'll see this is not going to work so hot. See, now we see points, just random points in here which the polynomial doesn't even interpolate. It doesn't even go through these points because now our errors have compounded so badly that the polynomial is not even the right answer anymore. So you can see how matrix operations can get hairy with huge matrices, and when you're paying attention to things like significant digits, which any computer is. There's our little side note for the day is numerical stability, and you don't really understand something deeply, I would say, until you can code it. And until you can code it scalably, is scalably a word? Until you can scale it up especially, that's when you will learn to understand something deeply. Thanks for watching.